Buenas tardes y muchas gracias por su asistencia a esta primera conferencia del ciclo que ha organizado la doctora Ana Chucarro, Conferencias de Astrofísica y Cosmología, la ciencia del cosmos. La ciencia en el cosmos. En primer lugar, desearía expresar mi agradecimiento al director de la Fundación BBVA, profesor don Rafael Pardo Avellaneda, y a la profesora doña Ana Chucarro, directora de este ciclo de conferencias, por darme la oportunidad de presentar al conferenciante de esta tarde, el profesor Samuel Chao Chung Ting, del Instituto Tecnológico de Massachusetts, e introducir brevemente el tema de la conferencia. Considero igualmente apropiado expresar también mi reconocimiento a la formidable tarea que la Fundación BBVA realiza en apoyo de la ciencia y en particular de la física desde hace mucho tiempo. Baste mencionar la relevancia de los premios Fronteras de Conocimiento, los premios de la Real Sociedad Española de Física y de Matemáticas y la celebración de ciclos de conferencia como este, que en su quinta edición inaugura el profesor Ting, y aquellos que están relacionados con la física de partículas elementales en colaboración con el CERN. Por todo ello, muchas gracias por esta ejemplar y magnífica labor. Y añadiría, y que cunda el ejemplo. El profesor Ting recibió en 1976 el Premio Nobel de Física por el descubrimiento de la partícula J en el Laboratorio Nacional de Brookhaven en Estados Unidos, institución en la que tuve la fortuna de trabajar desde 1969 hasta 1972 y en la que asistí por primera vez a un seminario impartido por nuestro conferenciante, en el que presentaba resultados muy precisos obtenidos en procesos de fotoproducción de mesones vectoriales originados en una serie de brillantes experimentos en el laboratorio alemán DESI en Hamburgo. El descubrimiento de la partícula J en noviembre de 1974, simultaneado con el descubrimiento de la misma partícula en Slack, en California, allí denominada Psi, por un equipo de investigadores dirigido por el profesor Barton Richter, con quien compartió el galardón de la Real Academia de Ciencias sueca, fue un hito verdaderamente extraordinario en el tortuoso camino de desentrañar la estructura íntima de la materia. El descubrimiento ponía de manifiesto la existencia de un cuarto constituyente fundamental de la materia, el quark C, y robustecía de forma casi definitiva la idea de los quarks introducida por Gell-Mann y Zweig en 1964, al tiempo que consolidaba el denominado modelo de quarks, uno de los pilares del modelo estándar de partículas e interacciones, junto con las ideas de unificación y rotura espontánea de la simetría electrodébil, libertad asintótica y profunda comprensión de la fuerza nuclear fuerte. Con anterioridad a este descubrimiento, el profesor Ting había participado en un experimento realizado en 1965 en el Laboratorio Nacional de Brookhaven, en el que se descubrió el antideuterón, la antipartícula del deuterón, que es el núcleo del átomo de deuterio. Aunque en 1932 Anderson había descubierto el antielectrón y en 1955 y 56, respectivamente, Segre, Chamberlain y Cork habían descubierto el antiprotón y el antineutrón, la idea de extender la noción de antimateria a sistemas nucleares formados por varios nucleones no parecía evidente ni era unánimemente aceptada. De ahí la relevancia de este descubrimiento. Tras el descubrimiento de la partícula J en Brookhaven, el profesor Ting continuó su carrera científica en el colisionador de electrones y positrones Petra del laboratorio DESI en Hamburgo. El experimento MAR-J, dirigido por el profesor Ting, fue uno de los 4 experimentos que en 1979 descubrieron el agente propagador de la interacción nuclear fuerte, el gluón. El estudio detallado de estos procesos tuvo enorme relevancia en la consolidación de la cromodinámica cuántica, la teoría que describe los procesos mediados por la interacción fuerte. En este mismo experimento, la observación de una simetría de carga en el par de muones resultante del proceso de aniquilación electrón-positrón constituyó una de las primeras y más significativas validaciones del modelo estándar electrodébil de Weinberg-Glashow-Salam. En 1981, ante la inminente aprobación por el Consejo del CERN de la construcción de un gran colisionador de electrones y positrones, denominado LEP, para el estudio de las propiedades de los bosones vectoriales Z y W+-, el profesor Ting aglutinó una gran colaboración internacional para la construcción de un experimento llamado L3, que fue uno de los cuatro que desde 1989 hasta el año 2000 estuvieron en funcionamiento. El legado científico del programa experimental de LEP es, sin lugar a dudas, extraordinario. En LEP se midió con una precisión del 1 por 100.000 la masa del bosón Z, con una precisión del 2 por 1000 el número de neutrinos ligeros. Se determinaron límites superiores para el tamaño de los quarks y los leptones. Se demostró la dependencia con la energía de la constante de acoplo fuerte, predicha por la hipótesis de libertad asintótica. Se pusieron de manifiesto la existencia de correcciones radiativas electrodébiles que confirmaron la naturaleza mecanocuántica subyacente del modelo estándar electrodébil y que permitieron precisar en 1992 la región de masas en la que debía materializarse el quark top y posteriormente a finales de los 90 acotar la escala en la que debía aparecer el bosón de Higgs, finalmente descubierto en el LHC del CERN en 2012. A principios de los años 90, el profesor Ting madura la posibilidad de construir un espectrómetro magnético de altas precisiones para el estudio de la radiación cósmica, con especial prioridad en la componente eléctricamente cargada y para ubicación en la Estación Espacial Internacional, un entorno libre de las complicaciones introducidas por la atmósfera. Una iniciativa abordada previamente sin éxito por prestigiosos investigadores. A pesar de las enormes dificultades técnicas y de toda índole, algunas en parte como consecuencia del accidente del transbordador Columbia en 2003, y sobre todo, gracias a la determinación y tenacidad de nuestro conferenciante, el 16 de mayo de 2011, la última misión espacial del transbordador Endeavour transportó el instrumento Ams a la Estación Espacial Internacional, iniciándose 48 horas más tarde el flujo de datos hacia los centros de control de operaciones en Estados Unidos y Europa, que permanece esencialmente ininterrumpido desde entonces. Es universalmente aceptado que el estudio de la componente electromagnética de la radiación cósmica neutra ha sido la herramienta fundamental para el acoplo del conocimiento acerca de la composición y evolución del universo. El descubrimiento de la radiación cósmica de microondas, sus asimetrías, ha permitido determinar la composición en materia y energía del universo, establecer su plenitud, así como el proceso de expansión acelerada, poner de manifiesto la existencia de una nueva forma de materia y energía, las denominadas oscuras, descubrir los púlsares y los púlsares binarios y la emisión de ondas gravitacionales, etcétera, etcétera. Otras formas de radiación cósmica neutra, los neutrinos, han permitido validar el modelo estándar del Sol, resolver el enigma del déficit de neutrinos solares y atmosféricos y establecer el carácter masivo de los neutrinos. Y más recientemente, la primera observación de las ondas gravitacionales ha añadido a otro poderoso mensajero para el estudio del universo. El estudio de la radiación cósmica cargada descubierta en 1911 y que tuvo enorme trascendencia en el desarrollo inicial y hasta bien entrado el pasado siglo, mediados del pasado siglo, de la física de partículas elementales o física de altas energías. Mantiene un interés renovado para estudiar con precisión aspectos fundamentales de la física moderna, contribuir a desentrañar la naturaleza de la materia oscura, buscar trazas de antimateria cósmica primordial, entender el origen de los rayos cósmicos y los mecanismos de confinamiento y propagación en nuestra galaxia, o poner de manifiesto fenómenos nuevos, son algunos de los fascinantes desafíos a los que se enfrenta esta disciplina del conocimiento básico. El experimento Ams, del que nos hablará nuestro conferenciante, es una poderosa herramienta para contestar algunas de estas fascinantes cuestiones. Desde 1981, gracias a una espléndida iniciativa del desaparecido Juan Antonio Rubio, un grupo de investigadores de la antigua Junta de Energía Nuclear, hoy CIEMAT, colabora con el profesor Ting, primero en el experimento Mar-J en DESI, después en el experimento L3LEP del CERN y desde 1997 en el proyecto Ams en la Estación Espacial Internacional. Gracias al profesor Ting, se ha formado en el CIEMAT un grupo competitivo de investigadores con reconocido talento científico y técnico, ampliamente contrastado a nivel internacional y con probada capacidad para integrar colaboradores industriales. Finalmente, quiero añadir que el profesor Ting ha recibido a lo largo de su extensa, exitosa e indesmayable trayectoria científica multitud de galardones. Uno de ellos, en 2004, el de antiguo académico correspondiente extranjero de la Real Academia de Ciencias Exactas, Físicas y Naturales. Thank you, Sam, for what you have achieved in fundamental physics and for your continuous support and advice to the CIEMAT group. For us, this has been of the greatest importance to become better scientists and to be in the position of doing better science. Now, the floor is yours.
Good afternoon. It is seldom for me to give public lectures. Once a while, I do that at MIT when they are in fundraising mood. And I'm very honored to be invited by both of you. So what I would like to do is to share with you an experiment on the International Space Station. The International Space Station, from this place to this place, is 110 meters. From here to here is 80 meters. So it's like a football field. It weighs 420 tons. The construction cost is about $100 billion. So you are economists, and so this is very costly, no immediate financial benefits. So on the space station, which is 420 kilometers above the Earth, rotating around the Earth every 93 minutes. There are 6 astronauts living on board, and on there's one experiment with Manuel Aguilar, Javier Verdugo, Carlos Manaea, and many others from CIEMAT, and people from MIT and many other countries work. So I want to share with you why we do this experiment, what we have found so far. Manuel Aguilar discussed the development of accelerators. The first accelerator is 1612, where Galileo did a very simple experiment, found gravitation. The energy is very low. This is the largest accelerator, LHC, extremely high energy. And the purpose is to study the fundamental building blocks of nature. This accelerator still exists, and you can visit them. So this is a picture of AMS inside the space shuttle. It was launched from Kennedy Space Center on May 16, 2011. It has two solid rockets, each weigh 1,000 kilograms. Just within 123 seconds, the two solid rockets burned off, and so it falls apart because you want to exhaust the fuel. Fuel is also weight. You want to remove them as quickly as possible. And then there are 800 tons of liquid oxygen and hydrogen will last for 8 more minutes, and then it's in space. And this part is fall into Indian Ocean. And so after a short time, then it's in space. This is not a cheap experiment. Somebody have given me this cartoon, which said, look, instead of sending your detector into space, send money to space is much cheaper. So the question is, why you do these things? The problem today, which challenge us, are immense. The question is, how can these challenges be met with the tools we have developed? I would like to read a short passage to you. Humanity is being ravaged by disease. Doctors are powerless against it. Pollution is everywhere. Men and women die daily in senseless ethnic conflicts. Homelessness is rampant. People can't read. Children are being killed on the street. And this was quoted in Europe in 1350. Not too far from what you read, some of the issues today. Yet from this period of despair, destruction, and disillusionment sprang the greatest period of hope, new ideas and creative expression. The Renaissance was born in Italy and spread throughout Europe, transforming how people look at the world and their place in it. Scientists re-examined all the ideas about the nature of the universe inherited from ancient Greeks and Romans. Modern science, or the understanding of natural phenomena using experimental techniques, was established during that time. In this century, we enjoyed unprecedented advancement in technological development, such as in the field of communication, computers, transportation, healthcare, and so forth, which have had dramatic effect on the quality of all our lives. What is often forgotten is that the foundation of this achievement was laid down some time ago by scientists who were driven by intellectual curiosity and not by economic concerns. So here is my little graph on fundamental science and society. So this is the physics in 1900s, this is 1930s, and this is what we have today. In 1900s, we studied classical physics, mechanics, thermodynamics, optics, leading to today's television and aircraft. In the 30s, we studied quantum mechanics and atomic physics, leading to today IT, laser, your cell phone, your internet. In the 40s, what is considered fundamental physics, and perhaps not useful, nuclear physics. Now it's used in reactors and isotopes. So accelerators goes to smaller distances. On the opposite side, in the 30s, we study stars, study sun, now used for navigation, your little GPS, and time navigation. The experiment CMR and I are doing is going to larger distances. So the physics now have extremely small distances and extremely large distances. So frontier science at extremely small distances, of course, at accelerators. And you're all familiar with the large accelerator. And this accelerator's byproduct is the invention of WWW and discovered many particles. From these studies, we know an atom outside is electrons. Inside the atom is the nucleus. Inside the nucleus are particles. Inside the particle are quarks. And this is after hundreds of years of study found there. So, as Professor Aguilar said, I've had many years of collaboration with Spanish scientists, and started July '81 with the late Juan Antonio Rubio and Javier Verdugo, Carlos Mañar, and many others. And these pictures of them, and you now do not recognize them. They have changed a little bit. So, as Professor Aguilar has elegantly mentioned, one of the Spanish accomplishments was work on the discovery of gluons. Gluon is the carriers of forces between quarks. Why you don't see quark? Because they're bound together by gluons. In nature, there are three types of forces. One is gravitation. Gravitational wave, after 400 years, finally has been observed. The electroweak are carried by light rays and these two other particles. Nuclear forces is carried by gluons. So this is a fairly important discovery. And this was carried out in the world's first large electron-positron experiment. And in this place, we built this detector and discovered the gluon jet. The second Spanish accomplishment is the experiment called L3. It lasts for many years, many physicists from many countries, and with a strong participation from Spain. The idea is very simple. You have a very large accelerator. You accelerate electrons, positrons. Positron is the antimatter of electron. So when a matter and antimatter collide, it produces energy and produce high temperature. If you have 100 billion electron volt electron and 100 billion electron volt positron collide, you produce the temperature 400 billion times the surface of the sun. The temperature of the light bulb, the voltage of a light bulb is 220 volts. Imagine you have 100 billion electron volts, so the energy is enormous. And so this means in the laboratory, in a controlled way, you produce the first billionth of a second of the universe. So if the universe comes from Big Bang, you try to reach in this region. People believe the universe comes from Big Bang. And so gradually, after 14 billion years, we have all of you and myself. Now the question is, what happened at the beginning? So what is the purpose of this experiment? I just mentioned, we now know the world is made out of point-like particles, 6 types of quarks, and something we call leptons, actually electrons. That means the ordinary electron from space, which is 200 times heavier, and electron in the nucleus, 4,000 times heavier, the ordinary electron. And its neutral, chargeless partners called neutrinos. So for a simple experimentalist, you can ask some questions. The first question is, how many types of electrons are there? Why there are only 3? How large are the electrons? Can electrons be divided into smaller particles? Similarly, you can ask, how many quarks are there? Why there are only 6? Why there are not more? What is the size of the quark? Can quark be divided into smaller particles? If you will ask a theorist, and they will tell you they know all the answers. But if you don't measure, if you don't check, you will never know. So this was the experiment where the Spanish and groups of other people together build, and this is one of the magnets. It's built in this way, different particles go through, leave different traces. So these are the detectors, which was very large detectors, and these are mostly made in CMR and at MIT. Those are very difficult device, very, very large, but very, very precise. So this is the front page of Scientific American, describe one of the events. There was, in 20 years, 300 papers about this thick, but in physics, the fundamental things can always be described in a few sentences. The result of the 300 papers can be summarized as follows. In the universe, there are actually only 3 kinds of electrons. Electron we know, electron from space, electron in the nucleus. There are only 6 types of quarks. To the energy that is available. And more important, electrons and quarks has no size. Their radius is less than 10 to the minus 17 centimeter. Less than is not equal to. 10 to the minus 17 is a very, very small number. If you were to close your eye to think about it, we use electricity every day, but we seem not be able to measure the size of electrons. These 300 papers have 300 results. They are in excellent agreement with the standard model, with the mass of the Higgs limit larger than this. This is unfortunate, because when your results agree with the theory, what you learn is very limited. It's only when your results disagree with the theory, you learn something. So let me now talk about this detector in space, and Manuel Aguilar, Javier Berdugo, and many others work on this experiment, made very important contributions. What is science on a space station? And this can be easily visualized but realized there are only two kinds of cosmic ray traveling through space. There are neutral cosmic rays, light rays, and neutrinos. And this has been studied for hundreds of years. Then there are charged cosmic rays. Because it carries a charge, it has a mass. Because it has mass, it's absorbed in Earth's atmosphere. And so to measure its original property, you have to go to space. Because it carries a charge, you need a magnet. Because only in the magnetic field, positive go one way, negative go another way. Now, put a magnet in space is somewhat difficult. Everybody remember the magnetic compass, and one end will point to the north, the other end will point to the south. So if you put a large magnet on the space station in no time will lose control. And so finally, we figure out a way to design a magnet that does not rotate in space. So a magnetic spectrometer like AMS on the space station, ISS means space station, is a unique way to provide precision, long-term measurement of high-energy cosmic rays. Together with us, there are very interesting experiments. This is an experiment studying neutrinos at South Pole. The experiment is located 1.4 kilometers under the ice, has a volume of 1 cubic kilometer. In there, after 1.4 kilometers, there are 5,000 detectors. And this, their control room, floated on the South Pole to detect neutrinos from outer space. There's another experiment used the fact when a very high energy charged particle goes through atmosphere, you interact with the atmosphere, you produce many secondary particles. And so if you put detectors, measure the secondary particle, you can find the energy of the original particle. In order to do that, in order to measure very high energy, you need a detector which is located in Argentina, a rather large area. This is the city of Paris, and this is the size of the detector. It's 10 times larger than the city of Paris. Measure extremely high energy particles. Of course, you will not know what is the property, what you study, because everything has broke apart. So what is this experiment on the space station? It is the first precision particle physics detector deployed in space to measure charged cosmic rays and study their characteristics. The cost, by NASA's counting, for the detector is not cheap. It's about $2 billion. And mostly come from Europe and Asia. The US contribution is to use the space shuttle to deliver this detector to space and use the space station. So AMS is now exploring new physics not possible to do on Earth. It is an international collaboration with major contribution from NASA, from CMR, CDTI, from German Space Agency, Chinese Space Agency, European Space Agency, Italian Space Agency. And there are many countries, many institutes, and many physicists. Recently, Turkey and Brazil has also joined us. Because it is a very costly experiment. So the government hesitated to proceed. And finally, the Congress of the United States in 2008 unanimously passed a law called H.R. 2028, H.R. 6063, asked the government to provide additional flight to deliver the alpha magnetic spectrometer and other scientific equipment and payloads to the International Space Station. So this is the first experiment required the support of the United States Congress. Because it was unanimously approved by both houses, so the administration will have to follow. Once it's over 2/3, it becomes a law. So this is a trillion electron volt spectrometer. Spectrometer is a device to identify different particles and their energy. Cosmic rays are characterized by their charge, namely their position on the periodic table, and something called rigidity, namely energy. I mean, rigidity is just a form people use, momentum per unit charge. You can think of it as a charge or energy. So this is a very precise detector. Nobody has ever done this before. Most people think it cannot be done. And finally, it's there. On the top is a transition detector. It's on the left side. Its purpose is to identify electrons and positrons. The electrons and positrons go through the detector, called TRD. It will give out a signal. And then there are 9 layers marked 1, 2, 3, 4, 5, 6, 7, 8, and 9 are silicon detectors, measure the track of the charge. And then at the end, it's called electromagnetic calorimeter. A calorimeter is something very simply understood. When a particle goes through a detector, if the detector is very thick, it soon loses all its energy, and you measure the energy. It's an energy measurement. And then there are 2 banks of a time of flight detector. One, you can see called time of flight, one in the top, one in the bottom, which measures the direction of cosmic rays. And then there's a magnet, measure the sign of the charge. And the one thing that was done, very important thing, done in Spain, is called ring image Cherenkov counter. Its purpose is to measure the nuclear charge and energy. If you look at this picture, you realize the charge, namely its position on the periodic table, and its momentum or energy are measured independently by 4 detectors. This is for many reasons. The first of which is once in space, if something goes wrong, you cannot send a graduate student to repair it. So you better make sure there's a redundancy. The second thing, it gives you an inter-check, inter-calibration. So the magnet, 10 magnets were built, because nobody has put a magnet in space. So when we build a magnet, we build 10 of them. The last 3 are full-size magnets to understand whether the magnet will fall apart when you do the acceleration. The second is you test the magnet to find out at what point it will fall apart. Because if you put a magnet on the space shuttle, if your magnet fall apart, it will not be very good because it will kill all the astronauts. And the third is the flight magnet. The magnet was made in China. That is because the best permanent magnet material is from Inner Mongolia, which at this moment is part of China. Transition radiation detector was mostly done in Germany. It identifies electron positron by something called transition radiation and nuclei by energy loss. And this is done in Aachen. This is why I know so close to Leiden. These are the silicon detector. There are 9 planes, 200,000 channels, measure the coordinate to 1/10 of your hair. It's a large international collaboration. And this enlarged view of silicon detector, coordinate resolution is 10 microns. The ring image Cherenkov counter, otherwise known as RICH, is to measure nuclear charge and velocity. Velocity means energy, to an accuracy of 1 part in 1,000. So these 3 graphs shows the measurement of aluminum, measurement of calcium, measurement of iron at extremely high energies in space. And these are mostly done in Spain. And this detector has 10,000 photosensors to identify nuclei and their charge. And this is CMR group who made this possible. So we also had excellent support from CRISA. So the detector is the largest of its kind ever put in space. It's 5 meter by 4 meter by 3 meter, weight 7.5 tons. This is the only experiment where the missile designers of China and missile designers of Taiwan work together. Normally, they do not. They hardly talk to each other. So during the shuttle launch, the Spanish Minister of Science and Innovation come to the Kennedy Space Center. So on May 19th, AMS was installed on the space station, and you can see 2 astronauts, one is there, another in the front. When they come out, it's always a pair for safety reasons. After it's installed, at 5 o'clock, after 4 hours of checking, fortunately, nothing went wrong. So we began to collect data. I would say we're rather lucky. So in 5 years, we have collected 80 billion cosmic rays. And this is much more than all the cosmic rays collected in the last century worldwide. So let me share with you a few physics results. Because it is a very precise particle physics detector, so the data analysis was always carried out by at least two international teams. And the ones put in red, Mr. Verdugo, and Carlos Mania, Jorge Casals, and Carlos Delgado, Alberto Oliva are from Spain. The first question we would ask is a search for the origin of dark matter. We know 90% of the universe is not observable. Because you cannot see it, that's why you call dark matter. A galaxy, as seen by the telescope, is on the left. But if you could see the other 90%, the galaxy will be on the right. Even though you cannot see it, but the collision of dark matter produces energy. Energy will go to ordinary matter, such as positrons, positively charged electrons. This excess of positrons can be accurately measured by AMS. So the excess positron is described as positron fraction, namely positron divided by the total number of electron positrons. So collision of ordinary cosmic rays will produce this green curve. And because in space, they're ordinary cosmic rays. But if you have dark matter, you will produce much more than collision of ordinary cosmic rays. And this red curve will correspond to you have dark matter with energies of different energies. You will see excess. So a deviation from collision of ordinary cosmic ray of the green curve means something new has happened. So this is our first result. This result was published in 2013. Sure enough, the red point, our measurement does not agree with the green curve. It more fit to the blue curve. So this get everybody excited. There's long articles in New York Times, in Wall Street Journal, in Spanish newspaper, in German newspaper, and many, many newspapers, and claiming incorrectly that we have seen dark matter. So a year later, we made much more precise measurement, and this time based on 11 million events. If you look at this red curve, you will think the following. At very low energy, the red curve and the green curve must agree with each other. Otherwise, your measurement has no meaning. And second, when the rate increases, it must agree with the theory. And then there must be a point when the energy stops increasing. Stop increasing is because dark matter has a finite mass. When you have a finite mass, you cannot produce infinite energy positrons. And then you have to look how quickly it falls down. A curve has normally 3 or 4 characteristics. And so let us look what we have seen. We indeed found the red point is our measurement as function of energy in billion electron volt. At very low energies, the measurement is agreed with collision of cosmic rays. But when the energy increases, it suddenly deviates from collision of cosmic rays. So the deviation from traditional understanding of collision of cosmic rays shows something new has happened. Now, what is this? What has happened? Our increase, we show, is different from collision of cosmic rays, and it agrees with pulsars and with dark matter. The energy is not high enough to distinguish the excess positron is from pulsars. Pulsar is a rotating neutron star, and because you have a strong magnetic field, a light ray, go into the magnetic field, produce electron-positron pair. And so that is another possibility. And so what the newspaper claim, not correct. We have results consistent with dark matter. We cannot rule out other possibility. Now the question is, where is the energy beyond which it ceases to increase? The lower curve is measured positron fraction. From this measurement, you can measure the slope. And so you will find out the slope increases, and then it's flat, and then decreases. It reaches 0 at 300 billion electron volt. When the slope reaches 0, means you no longer increase. So you have now found the highest point, it increases. Again, many newspapers, many media are very excited, incorrectly. So it will take us some time to finish the measurement of the last part. To find how quickly it falls down, it will take 5 more years. In 5 more years, we will know if it's pulsars, it will be the blue curve. If it's dark matter, it will be this semi-red curve. So it will take some more years. The important thing is the data agrees with dark matter prediction or the measurement, but this does not prove you have found dark matter. You need a few more years to distinguish whether it's come from pulsars, from a new type of pulsars, or from dark matter. The next measurement is electron and positron spectra. Spectra is energy, the number of particles produced as function of energy. The blue is electron data, the red is positron data. You look at this curve, the errors are enormous. But these were the best measurement in the last century with balloons and with satellites. Nevertheless, the data has large errors, and if you look at this data, they are inconsistent with each other. Because the data has so large errors, it has created many, many theoretical models. This is the AMS measurement. You look at this data, you will see the data clearly exhibit the different behavior of electrons and positrons, both in their magnitude. The magnitude for electron is on the left, for positron on the right, and their energy dependence. You would think electron and positron are similar things at high energy. They should be the same, but they are not. This is the measurement of protons before AMS. Protons are the most abundant cosmic rays. And these were the best measurement over the last 100 years. Nevertheless, the data have large errors and do not agree with each other. This is the measurement of protons based on 300 million protons to very, very high energy. And this measurement is to an accuracy of 1% because it's so difficult to measure. So there are 4 groups to do this: the CMR group, the MIT group, and there's a group from France and a group from Taiwan to do this. Only when the 4 groups agrees with each other to 1%, then we publish the data. What does this group, what does this data mean? The blue shade is the traditional understanding. This is the traditional understanding, traditional assumption. The data, the red point, agrees with that until here. After this point, the data moves, and so you have unexpected new contribution. Shows the traditional assumption is not correct. This is the measurement of helium before AMS. Helium nuclei are the most abundant cosmic rays, are mostly produced in supernova explosions. And these are the best measurement over the last 100 years, and you can see the error between them are very large. This is our measurement based on 50 million events, again by 4 international groups. If you look at this measurement, the data agrees with traditional assumption up to a point. After this energy, the data goes up. So this is unexpected. And so this is the first result on the measurement of the first few elements on the periodic table. The important thing is the measured rate different from traditional understanding at about the same energy. So this new observation contradict to the current understanding of cosmic ray behavior. Both proton, helium, and lithium. So all these results have changed the understanding of cosmic rays. Again, many articles appear, try to explain them. So the latest measurement of positron fraction, the behavior of flux of electrons, positrons, protons, helium, and nuclei is providing new, precise, and unexpected information. The results have changed our understanding of cosmos. AMS will be on the space station till 2024 or 2028. And in the next few years, the first most important thing is to measure to highest energies to understand what is the true nature of dark matter. And we will also look at the existence of antimatter and continue to search for new phenomena. If you remember what I said, everything we measure contradicts with previous understanding, both theoretically and experimentally. What do you mean, existence of antimatter in the universe? The Big Bang origin of the universe required matter and antimatter to be equally abundant at the very hot beginning, because that's the simplest way it could have come from a vacuum. So the universe now is 14 billion years old. You have this podium, have all of you. Another question is, where's the universe made out of antimatter? We know antimatter, heavy antimatter, does not exist in our galaxy. Because if it exists in our galaxy, it collects with matter, will produce sharp X-rays. The fact we do not see the sharp X-ray, sharp energy, means it does not exist in our galaxy. But the universe has 100 million galaxies. So the purpose for us is to look to every one of them, and until near the age of observable universe. So we know a universe have helium, carbon, nuclei, I already described. The question is it possible quite far away, there's the anti-universe of anti-helium and anti-carbon. How do you detect antimatter? Cosmic antimatter cannot be detected on Earth because matter and antimatter will annihilate each other in the atmosphere. Matter and antimatter has opposite electric charge, so you need a magnet to distinguish positive from negative. To do that, the first thing you do is to make sure your detector can measure all the elements in the periodic table in space. Now we have mapped out the element in periodic table. This we know is on the ground, and the first question is, does it exist in space? Is your detector sensitive enough to look for that? So that's a calibration, make sure you have confidence in your detector. So next question is, how do you, whether they are particles with negative charge? These are all positive charge nuclei. The experimental work on antimatter in the universe, because it was so difficult, not possible to put a magnet in space, and because of limited balloon experiment. So in 1967, a very well-known Russian physicist, Andrei Sakharov, proposed maybe antimatter universe does not exist. In order for it not to exist, you have two assumptions. The first, the symmetry principle, one of the fundamental principles in physics, maybe it's wrong in a major way. And second thing is the most abundant cosmic ray, protons, actually do not live forever, it actually decays. If these two assumptions is fulfilled, then you have a way to explain why antimatter disappeared. Over the last 50 years, many experiments, including the experiment at CERN, including a huge underground experiment in Japan. By the way, this is a boat. And this is an underground cave. People feel the water, the boat goes out. Eventually you get out. So nobody after the 50 years have found a strong symmetry breaking or proton decays. So no explanation found for the absence of antimatter. So experimentally, there's no reason antimatter should not exist. What my Spanish colleague and myself and others want to do is forget about this. Let us do a very sensitive look whether this exists or not. So, cosmos is the ultimate laboratory. Cosmic rays can be observed at energies higher than any accelerator. But the most exciting objective of AMS is to probe the unknown, to search for phenomena which exist in nature we have not imagined nor had the tool to discover. In fact, so far, all I have presented to you fit into that category. So let me go back to what I said at the beginning, the relationship between fundamental science and society. This pyramid has grown with new application at its end. And the fundamental research continually widen in spaces, go to larger distance and smaller distance. So the role of basic research implies it finds itself always in the outermost corner of the pyramid, hence it's sometimes viewed as being remote from daily life. Only after some time, when application develop and the public become familiar with new phenomena, does the value of basic research become understood. So to summarize, The prime motivation for basic research is our curiosity, the innate passion to learn something new and obtain a deeper understanding of nature phenomena. Results of basic scientific research, though difficult to predict in advance, have had a profound effect on society. Thank you.